Good morning friends. Today we will see solutions of rest of the numericals of root locus which we have started in control system tutorial CST-1. In the last part we have seen solution to first two numericals which were really important, and in this particular session we will see solution of all the numericals which are left out. These numericals are basically relatively easier than that of numerical number 1 and numerical number 2. So here we will not focus on the full procedure to solve the numerical, but we will just see what is the final answer and what is the important key point which you encounter while solving this problem. Okay, so let us start. So according to the question number 3, we are having a given GS and given HS, and we need to draw a root locus when the k varies from 0 to infinity here. So it is basically a question of direct root locus. Clear? So let us approach this question. So the first thing what you will do, you will try to find out the number of poles and number of zero, and at which point the poles and zeros are basically located. So we'll find that we are having one pole here, this pole, and this pole is at -2. Then we'll have a second pole at -6. Here is a second pole, and 1 0. We will find that 1 0 is located as -7. Clear? So after locating the poles and zeros on the real axis, you will try to find which portion of the real axis are basically parts of root locus and which portions of the real axis are not parts of root locus. How to locate these points? What you are required to do that, choose any point between the segment. Means if there between these two poles and between this pole and zero, and beyond this zero and beyond this poles are basically the segments. So if you choose any point between this segment and you'll look towards right of this point, you'll find that there is just one pole. So the rule says that if the number of poles plus number of zero is odd, then that particular point and hence that particular segment will be the part of root locus. So here it is odd, that's why this portion is basically parts of root locus. For this portion, basically two poles are there. 1 plus 1 is a 2. There is no 0, so it's a even. So these portions of the real axis is not part of root locus. Coming to this section, once again 1 0 plus 2 poles, that will be equal to 3. So odd. That's why this whole section will be the part of root locus. One more thing we are required to note, that there is a 0 on the left side of the S plane and on the real axis, and there is no any other poles or 0 on the real axis, right? And the whole of this section means towards infinity, between -7 to -infinity, is a part of root locus. In that particular case, we know from our experience that there might be a breakaway point, and technically speaking there might be a break-in point. Clear? So let us take a green color and then try to draw it. So this is basically one of the root locus. It will tend towards infinity. Clear? Exactly -infinity. So what happens basically, we are having k is equal to 0. The root locus starts at k is equal to 0. So we are having two poles. Root locus starts at poles with k is equal to 0. When you will keep on increasing the value of k, the roots of closed loop system will moves like this. At a particular this point, you will encounter it's a breakaway point, and this point is basically, it has been found to be s is equal to -4 0.76. If you will calculate the breakaway point, one of the breakaway point is this one and second is this one. S is equal to minus 9.23. Clear? So this point. Okay. So what is happening here? When it starts moving, when it encounters a breakaway point, then it will split towards this path. Note that we have taken the two colors, one is green and second one is blue. So this will keep on moving like this. If you will further increase the value of k, this will go here. Once again it will encounter a break-in point and then it will deflect towards this. So I have shown a multiple arrow. So many arrows are here, right? So that the movement is clear to you. You know that you draw a root locus with the help of open loop system, but it is basically shows the movement of poles of closed loop system. Clear? Similarly, when you will keep on increasing, one of the branch will move like this. Okay, this will like this. If you will further keep on increasing k, this will move like this, this, and this. This is basically what? This is movement of one of the root of characteristic equation, and hence you can say the closed loop poles. At k tends to infinity, and exactly at k is equal to infinity, it will merge towards this 0, and here also at k tends to infinity, this will go towards minus infinity. Clear? Okay, but how come you know that this is a circle? Basically, first you will start drawing the root locus by rules. So when we follow the rule, one of the rules says that you need to find the intersection of root locus with j omega axis. For finding the intersection of root locus with j omega axis, what you'll do, you you create a row array in terms of k, then one of the row will be the row of 0, and that will give you the value of k that will be equal to k is equal to k marginal. So if you will find the value of k marginal for this point, you will find the value turns out to be minus 8. So what it signifies? It signifies that at k is equal to, that value of k is equal to minus 8, the root locus will intersect with this j omega axis. But recall that we are drawing the direct root locus, which says that the value of k should be positive, means between 0 and infinity. But here the value of k is minus 8. It signifies that the root locus will never intersect that j omega axis. Clear? So this is a basically takeaway from this question. Whenever you find the value of k marginal to be negative, you are you become 100% sure that this root locus, whatever it may be, whatever the shape may be, it will never intersect this j omega axis. And see, the final root locus justifies this point. Clear? And we also know that since one breakaway point is here and second break-in point is here, so you'll know that automatically it will going to be, both these branches will going to be separated from this breakaway point and going to merge at this breakaway point. Clear? And one will move towards 0, one of the 0 which is located at minus 7, and another will move towards infinity. So hence question number 3 is over. Now coming to question number 4. Question number 4 says that the open loop transfer function is given by a given expression is there. We say k into s plus 12 divided by s square. S square is here, right? So s square signifies we are having two poles at origin. Clear? S square multiplied by s plus 20. Escape the root locus when the gain varies from 0 to infinity. Clear? Once again, we are asked to draw the root locus when the value of k is 0 to infinity. It means direct root locus. So first of all, try to find the value of poles, where our poles are located. So if you will try to find the value of poles, you will find that poles are located at one pole, because it was s square, so we'll have two poles at origin. So one pole and then second pole 0, and then the third was at minus 20. So let us first uh, locate these things. Here it is one pole, and I'm going to take a far away point is a minus 20. Here it is a minus 20. One more pole is there, that's why I'm going to take different color to show it. Let us take red color. So one more pole is here. So there are two poles at origin. Clear? What about 0? Coming to zeros, you find that there is only one 0, and that lies at s is equal to minus 12. So here it is a minus 12. Clear? There are no other poles in 0. So what will be the number of asymptotes? The number of pole is basically 1, 2, 3. 3. Number of 0 is basically 1. So number of branches of root locus will be greater than p and z. That will be equal to maximum of p and z, and that is equal to 3. And what will be the number of asymptotes? Number of asymptotes will be p minus z. Clear? So the difference between basically the maximum one and that minimum one, so that will be equal to 2. So when when we try to find out the angle of asymptotes, we find that the angle of asymptote is basically one is 90 degree and another one is like that. So corresponding asymptotes will be 190 degree and 270 degree. Clear? And if we'll try to find the intersection point of these asymptotes at real axis, you will find that the intersection point lies at minus 4. Clear? So we will have two asymptotes here. So let us try to draw these asymptotes. So we are having two asymptotes. Number one asymptote is like this. So I'm just taking some broken line to draw this. So number one asymptote is like this. This is the angle of 90 degree, and symmetrically the another asymptote will be on the other way at 270 degree. Clear? So these are basically asymptotes. Now after finding the asymptotes, what you will do, you try to find out breakaway points. But actually in this particular question there is no need to find breakaway point, because you know that there are two poles at origin. One of the pole is sitting above the other poles. So basically the two poles will be separated as soon as the value of k increase from 0. So say let us talk about this one, red one. So at k is equal to 0, there are two branches will start from here and one of the branch will start from here. So when the k will keep on increasing, this will terminate to this 0, and here when the k will keep on increasing, this will go like this. Clear? And another one, the blue one, will move symmetrically to the downside like this one. Clear? So this will be like this. So this basically, these 2 points, 2 poles are on the origin. That's why this is also a breakaway point. Without any calculation, you can say that this will be act as a breakaway point. So number of arrow, direction of arrow will be like this. Always try to show direction of arrow, right? So when k tends to infinity, this is here. When k tends to infinity, here it is also when k tends to infinity, and when k is equal to 0. Clear? So this particular question is also clear to you. Coming to question number 5, it says that determine the open loop transfer function for a given root locus plot shown below. It will be shown in the next slide. And determine the range of k for stability. you were provided with a root locus plot, and you were asked about the range of k for the stable operation, and also you need to find forward transfer function if feedback transfer function is given like this. So let us first see what is given. So here is a given that uh, here we are having a pole at origin, then we will have second pole at -1, third pole at -2. So, and this is basically a breakaway point. This is like this. The direction of movement of roots are like this, and this particular point, the intersection point, is basically given to be 1.414 j, and symmetrically this point will be -1.414 j. So first we need to find the range of k for a stable operation. To find the range of k for a stable operation, we need to find the open loop transfer function first. Then with the help of open loop transfer function, we will try to find characteristic equation, and then we'll form a row theory. So first try to find the open loop transfer function. We are having open loop transfer function GSHS, that will be equal to numerator upon denominator. So first talk about denominator. We are having pole at origin, so S, pole at -1, so S plus 1, and third pole at -2, so S plus 2. So we are not having any 0, so the numerator will be 1, but we will have a variable gain k, so 1 multiplied by k, that will be equal to k. So characteristic equation we denote by QS. This is basically a standard denotation, that will be equal to 1 plus GSHS, that will be equal to 0. So putting the value of GSHS from this above expression, what we will find? We will find that characteristic equation QS will become basically S cube plus 3s square plus 2s plus k, and that will be equal to 0. Clear? So now we need to find row theory. Why we need to find row theory? Because we want to find the k marginal. Why we need to find the k marginal? K marginal is basically the value when the root locus intersect with j omega axis. Because when the value of k will be greater than k marginal, means for this portion, this blue portion, this portion, when value of k is greater than k marginal, right? Accordingly here also the value is greater than k marginal. So for this portion and all other portion like this, the root locus lies in the right half of the S-plane, and hence the system becomes unstable. So for stable operation, the value of k must be less than this k marginal. So k should lie on this side. Okay. So to find k marginal, we need to form a row theory like this. Clear? So first the highest power is s cube, so we'll take s cube, then the second highest power is s square, then s to the power 1, then s to the power 0. The coefficient of s cube is 1, so we'll jump this thing. You know that how to form a row theory. So we'll take 2, then this thing, this, so 3, then k, then performing the cross multiplication, 3 multiplied by 2 will be equal to 6 here, 1 multiplied by k will be equal to k divided by this pivot element 3, right? And if nothing is here, you will consider 0 is here. So once again 3 multiplied by 0 will be 0, 1 multiplied by 0 will be 0, divided by pivot element is 0 divided by 3 will be 0. Clear? Second one, this whole term means this 6 minus k divided by 3 multiplied by k minus 3 multiplied by 0. So 3 multiplied by 0 will be equal to 0. So the only term in the denominator is 6 minus k divided by 3 multiplied by k, and once again whole term will be multiplied by this pivot element 6 minus k divided by 3. So we'll get k here and 0 here. Clear? So we need to find the value of k for the stable operation. So you need to find the row of zeros. So what you'll do, you can't take this value k is equal to 0, because when you will take k is equal to 0, the root locus is still at the at that poles only, right? So you need to take any value which is greater than 0. So this k will not be 0, so the row of 0 will be given by this row only, because one value is already 0 and you can manage this term to be equal to 0. So if this term will be equal to 0, then we will have row of 0. So this will lead to k will be equal to like 6, right? So this k, we say that this is basically k marginal. So what will the value of k marginal? This will be equal to 6, here 6. So the first thing says that the value of k should be greater than 0. Why? Because we are tracing the root locus for k greater than 0 and less than infinity. So k should be greater than 0 is the first condition, and the second condition says that k should not be greater than k marginal, means k should be less than 6. So the second condition will be like this. So both 1 intersection 2 implies that the k should be, this implies k should be 0, between 0 to 6. So this is your answer to the first part. So for a stable operation, the value of k should be greater than 0 and less than 6. What about second part? Second part says that find the forward path transfer function if hs is equal to that much. Okay, so we are having GSHS will be equal to what? GSHS, we are having k divided by s into s plus 1 into s plus 2, right? So we are having GSHS is equal to k divided by s into s plus 1 into s plus 2, and we need to find GS. So you are required GS, so you will divide this whole term by HS. So if you will divide whole term by HS, so GS HS divided by HS, and HS is given to you here. Here HS is given to you. So you will have k divided by s into s plus 1 divided by s plus 2, and this whole term will be divided by s plus 0.5 divided by s plus 1. So s plus 1 will be cancelled to this s plus 1, and which will lead to k divided by s into s plus 0.5 multiplied by s plus 2. Clear? So this is the answer to your second question, right? Now coming to question number 6, we are given a open loop transfer function, and we are asked to sketch the root locus for the corresponding open loop transfer function. Since here nothing is given about the value of k, we will consider the value of k to be between 0 to infinity, and hence the corresponding root locus will be a direct root locus. So for the first, for the given system, our first job is to find the value of poles. So the poles will be basically given by this, the denominator, putting the denominator equal to 0. So we will get s is equal to 0, s is equal to minus 4, and then S is equal to, we are having two complex poles, minus 2 plus minus J4. So these are basically poles. So number of poles are basically 4. So 2 here and 2 here. So value of P will be equal to 4. Since there is no 0, so value of Z will be equal to 0. And hence the number of branches of root locus, which is maximum between P and Z, that will be equal to P, that will be equal to 4. And the corresponding number of asymptotes will be equal to P minus Z, and that will be equal to 4 minus 0, that will be equal to 4. Clear? So we are having 4 asymptotes. So we need to find the values of angle of asymptotes, means the angle which these asymptotes are making with the real axis. So the angle of asymptote is basically given by theta is equal to 2q plus 1, if you recall the formula, multiplied by 180 degree divided by mod of P minus Z. Clear? So using this formula, for the value of Q is equal to 0 to P minus Z minus 1, we will find the values of theta will be equal to 45 degree, means theta 1 is equal to 45 degree, theta 2 will be equal to 135 degree, theta 3 will be equal to 225 degree, and theta 4 will be equal to 315 degree. Clear? So now we are having the angles which these asymptotes make with the real axis. Now we need to find the centroid. Centroid is basically the point at which these asymptotes converge. Right? This is basically common point where they intersect on the real axis. So this is basically denoted by sigma, and sigma is given by summation of real parts of poles minus summation of real parts of 0 divided by P minus Z. So summation of real parts of poles, the first pole was 0 plus second pole was minus 4 plus we were having two complex poles with the real parts minus 2, each minus 2, so minus 2 plus minus 2. So these are basically summation of real parts of pole. Since we are not having any 0, so we will take the summation to be equal to 0 and divided by P minus Z, that is 4 minus 0. So this will be equal to how much? Minus 8 divided by 4, that will be equal to minus 2. So the asymptotes will intersect on the real axis at s is equal to, at sigma is equal to minus 2. Now we need to find the values of breakaway point. For finding the breakaway point, what we do, we form the characteristic equation. We are having GSHS given to us, so we'll form a characteristic equation which will be given by 1 plus GSHS is equal to 0. Then after forming the characteristic equation, we'll rearrange this characteristic equation such that we'll have k one side of the equation and rest all other things on the other side of the equation. So after performing those tasks, we'll have k will be equal to minus s to the power 4. I'm directly writing here 8 s cube plus 36 s square plus 80 s. So since we are interested in finding breakaway points, so we'll differentiate this value of k with respect to s and put this differentiation equal to 0. So dk upon ds will be equal to minus 4s cube plus 24s square plus 72s plus 80, and putting this whole term equal to 0 will lead to the value of s, which will be given by s is equal to minus 2, then s is equal to minus 2 plus minus, we are having cubic equation, so one of the root is real and the rest, the rest of the two roots are basically complex conjugate. So J 2.45. Okay, so we are having these three breakaway points, right? So now let us try to locate all these points on the S plane. So coming to the next diagram. So we were first will try to locate the poles on the S plane, and then we will try to locate these breakaway points. So first pole we are having a pole at origin, then second pole we are having pole at -4, and rather than that we are having two complex conjugate poles, that was -2 plus -4j. So each is having the real part -2, so we are going to locate this as a -2. I am going to say this point is -2, and I am going to take a dotted line for our reference, right? So I'm going to take a dotted line here, like this. This is basically dotted line for our reference. Okay, and we were said that we are having two more complex poles, that is equal to -2 plus -4j. So I'm going to say this is -1j corresponding -2j, sorry, plus 1j plus 2j, and here plus 3j, and here plus 4j. Equivalently here it will be -j, -2j, -3j, and -4j. And we were said that we are having a complex poles also. So I am going to locate this pole. So here we are having a pole. So pole at -2 plus 4j is a one pole, -2 minus 4j in another pole. So we are having four poles located. Once again I am telling, one pole at origin, second pole at -4, third pole at -2 plus 4j, and fourth pole at -2 minus 4j. Clear? Now applying the thing that which portion of the real axis is a part of root locus. So if you will take any point in this segment, means between -2 and 0, and if you try to look towards the right side of it, we will find that the number of poles plus number of 0 will be equal to 1 plus, there is no 0, so 1 plus 0 is equal to 0, which is odd. That's why this portion of root locus will lie on the, this portion of real axis will lie on the root locus. Coming to this portion, if you will look towards right, we'll have three poles, 1, 2, and 3. So three poles. So 3 is once again odd. So we'll take this portion also basically part of root locus. Clear? Also one point I would like to put it into your notice, that the presence of either complex poles or 0 doesn't change our decision about which portion of the root real axis lies on the root locus, because complex poles or 0 always occurs in pairs. So if for this particular, for example, say the p plus z is equal to odd, and for this portion that particular value of odd plus 2 will be also odd, means here it was 1 and here it was 1 plus 2 is equal to 3. So once again it will remain odd. So no need to consider basically this complex poles or complex 0 while deciding the portion of root locus which lie, the portion of real axis which lies on the root locus. Just need to see real poles and real 0. So accordingly we'll have this portion. Now we come to know that we are having basically uh, uh, three breakaway point. One breakaway point is at -2, and two other breakaway points are there that also lies at -2 plus minus 2.45 s. So 2.45 I'm going to say here, 2.45 j I am going to say. Accordingly, here it will be minus 2.45 j, and our calculation says that here means at this point, and from here also say here. So here and here, this red dot signifies that there must be a breakaway point. Okay. So at k is equal to 0, the root locus start from here and move towards -2. Here also at k is equal to 0, root locus start from -4 and move towards -2. So if you'll keep on increasing the value of k, the root locus will move and come closer. And since k is a breakaway point, so root locus will diverge. So it will divert like this, and one branch will divert like this. Okay. We are not having any idea how they will proceed, but we know that they will divert symmetrically. But from our previous calculation, we come to know that there is also a breakaway point here and here. Since breakaway point always lies on the root locus, so this root locus must need to proceed here. And the breakaway point, at breakaway point, we must have two branches merging, and then diverting from that point. So this also at k is equal to 0, while increasing the value of k, this will move like this. Okay. Similarly, that will move like this will move like this, and here they will divert. One will go like this, another will go like this. Here also one will go like this, another will go like this. We don't know where they will proceed. Now we need to find the value at which this root locus will intersect with j omega axis. How come you will find the value, that value? You will first find the k marginal. For finding the k marginal, you will construct a characteristic equation. Then with the help of that characteristic equation, you will form a Routh array, and with help of that Routh array, we will try to seek a row of zeros, and with that particular row of zero, we will have a value of k marginal, right? So putting that value of k marginal and forming auxiliary equation will lead to the point at which this root locus intersect to the j omega axis. So that point is found to be, I have calculated that particular point, and that particular point is 3.16 j and minus 3.16 j. Clear? So this root locus is going to bend. So it will bend like this and it will pass towards like this. So this will also bend like this, and this will pass like this. Clear? Since the root locus is always symmetrical in nature, so this branch is no way different from this branch. So this will also move like this. This similarly, this branch, this left branch is not any way different from that right branch. So it will also move like this. Clear? So we see that the root locus start from these four poles. First they encounter a breakaway point here, and then one move towards upper side, another move towards down lower side, and they also encounter a breakaway point here and here, right? So I would like to give you a BK concept when you encounter such type of question, because this type of question is a class of problem which you may encounter, and you may face it difficult to decide how many breakaway points are there, because when we try to find breakaway point, we just look at the portion of real axis. Means we are having a notion that the breakaway point will always lie on the real axis, but it is not so. It is certain that that the breakaway point will lie on the root locus, but it is not sure that the breakaway point will be always lie on the real axis. It may be anywhere in the complex plane. Like one of the root locus point, one of the breakaway point is at -2, which is of course on the real axis, but these two breakaway point are basically complex breakaway point which basically do not lie on the real axis. This is basically real axis and this is basically j omega axis. So let us have a BK concept here so that such type of question uh, will not make you in trouble. So the BK concept says that when the average of real poles, right? Average of real poles. What is the average of real poles? So real poles is basically two poles are real poles. One is at 0 and another one is at -4. So the average is equal to what? -4 plus 0, and since it is 2, so that will be equal to -2. So the average of real poles is equal to real part, okay, real part of complex poles, real part of complex poles. If there is a so what is the real part of complex pole? Real part is these are basically complex pole, this pole and this pole, these are basically complex poles, and the real part is -2, right? So whenever the average of real poles is equal to real part of the complex pole, the number of breakaway point will be 3, otherwise the number of breakaway point will be 1. Clear? So with this, we'll stop here, and I hope you will find this tutorial helpful. Try to revise and see the concepts which we have encountered while solving this tutorial. uh, Problems which you may face in the examination will be similar to that. We have covered almost all the concepts of the direct root locus in this tutorial.